Okay, we are real quickly going to go over how to find the equation of a line based on scientific data as opposed to just a normal math class again. Now, you might say, why is it different at all? Kind of the same sort of conversation that we had about graphing. If this is the data for a circle lab, usually what you do is you take two data points straight off of the data set. Okay, I don't have a data set for this sitting in front of me, but basically you take like a point here and a point up there, and you'd use your general equation, which we'll remind you of here in just a second. The problem is, this, as we talked about with graphing, is more likely to be an actual set of data that you're going to use, and as we talked about last time, there's going to be those little bits of error right there. So the problem is, if you use those particular data points as, just pull it straight off of the data, just the numbers that are sitting on there, what you're doing is you are assuming that they are done perfectly, which is, as we discussed last time, never going to be the case. So let's say, for example, that little guy right there, which obviously you can see has a decent amount of error, and this little guy right over here, say they have a decent amount of error. Let's say you use those two data points. Well, the problem is that what's going to happen, if I can get this correctly here just real fast, is that you are going to find the equation of the line in red, which is, of course, not our data. It's, not our line. Our line is the blue one here. This red basically assumes, when you take those two data points, it assumes that those two data points were measured perfectly, or it just tells you the equation based on those two. Okay. Now we are trying to find the equation of the entire data set, or the line of best fit. The blue guy here that you notice is a little bit off. So what we're going to do instead is that we have to pull data points straight off of the line. Okay, not the numbers that you give yourself. Okay, now if, for example, like actually, unfortunately, I just crossed it off. If you have like that little guy like right there, okay, sorry, it's hard to see. If you have a data point that falls perfectly on the line, you can use that. Otherwise, what you're going to want to do is easiest spots, of course, are just to find crosses like this that are really easy. Now, as you can see, that spot is 3 centimeters in diameter and 10 centimeters in circumference. I'm going to go ahead and write that down. Not a bad idea. Let's go ahead and use a different pen, because that's not going to be super clear. Okay. 3 centimeters, 10 centimeters. My apologies on centimeters being a little confusing. Do remind yourself that it is usually x, y. Just general formula right there. Okay. Then let's go ahead and find another data point. Now, when you find the second data point, it's a good idea to actually spread your data out as far as possible. You do not want to take just like the next point here, even if it's super clear. Okay. Similar reason to the reason why we want a decent sized graph. We want to spread it out as far as possible. Minimizes that error. So I'm going to come somewhere over here, and I think, what point did I end up using? Make sure we're good here. I think that's it here. Oh yeah. Okay, I'm right. 70. And yeah, okay. Again, I'm not worrying about the dot. I'm going off of the line here. So that dot ends up being, I think, let's go straight down. Is that 23? 21? Let's check here. 20, 24. Yeah, 24. Look at that. So here we are. That is 24 centimeters, 70 centimeters. Okay. So you have to get 2 points off of the line, typical to what you have to do to find the equation of line in general. And this is the work that I've already done for it. All right, so here are my 2 points right here, 3, 10 centimeters and 24, 70 centimeters. This was just to show you that I pulled them off of the graph and not off of the data. Okay. Now, here is your general formula for a line, y equals mx plus b. You should know this. The m is slope. Slope. You are probably very used to saying rise over run, and that's not bad to get you here, but for reasons that we will talk about, especially when we get into velocity, you need to learn that this guy right here is actually called change in y over change in x. How much it goes up the y relative to how much goes on the x, just comparing the two of them. And the way you get that is you just take y2 minus y1 and x2 minus x1. We'll talk more about those in the future as well, but here I just plug that in. Which one's y2? The later one. So what's the later y? That's my 70 centimeters minus my original y. So I got 70 minus 10. And then I do my x's. The later x, x2 minus the earlier one, 24 minus 3. And I get 60 over 21, which ends up being 2.86. Now, what you'll notice that I always do, and I commented on this the other day, anytime I write a number, almost every single time I write a number, it's got the units next to it. That being said, this says 60 centimeters over 21 centimeters, and therefore the centimeters cancel, and that would actually make this guy unitless. One thing I'll harp on is when you write numbers, they should always have units. I said that already, but in this particular case, it actually does not have units because they cancel, which you can see very clearly if you carry them along. All right, now, what we're doing here, when I say find the equation of the line, as I should say, we're trying to find the specific equation of the line. That's always the general equation of every single line that ever exists. So when I say I'm trying to find the specific equation, really what that comes down to is y and x are always going to be your variables. What we're trying to do is we're trying to find what are those two constants. So what we just did very quickly is found the slope of this particular guy, or the m constant right there, 2.86. And so now we just need to find the other constant, b. Oftentimes, b will appear on your graph to be 0, as it does actually with my graph right there, really darn close to 0. Okay, I don't want you to estimate this. I do in fact want you to calculate based on your numbers what that actually is. So the way you do that is after finding the slope, which you have to do first, you come right down here to your general form of the line, and basically, just like any algebra problem, if we're trying to find one thing, we need to know everything else. So m, you'll see notice right below, is my 2.86. So I just calculated. Okay, and y and x could be either one of these pairs. I usually choose the larger pair, but it could be the other one as well. So I plugged in y was 70 centimeters, my m was 2.86, my x was 24 centimeters, and then I just do some algebra. Multiply. Actually, I think I subtracted them first, but you can multiply first, subtract underneath, and you get that b is calculated to be 1.36, which does in fact match with where my graph is at. Pretty darn close to that, but I get a lot more accurate answer. Okay. Last piece is to give the specific equation of the line. You'll notice that one thing that I do first is I change what the y is and what the x is. That's because as we are dealing with data and not just generic y's and x's, y is circumference, and so I just chose C, x is diameter, so I chose D. I would like you to do that when you come up with the final equation of the line. And then, of course, you just plug in here 2.86 for my slope, which does not have units, so I don't put units on it, and 1.36 centimeters, which, of course, we got from this guy right here. That's how you find it.